In this video, we will do med calculations. We will look at three different methods to complete the calculations: the nursing formula, a proportion, which is two equal fractions, and dimensional analysis, where we cancel the units. Let's get started with an example. The first piece of information the nurse needs is what the doctor has ordered. Here the doctor has ordered 200 milligrams of acetaminophen as needed every 4 hours. Next, the nurse needs to know what is available. So we have the label from a medication. Most important piece of this label is the strength of the medication, called the dosage strength. It's here in the dark box. So 160 milligrams per every 5 mLs. Now we're ready to start our problem. We can use any of the three methods. In the nursing formula, we start with the doctor's order, or the desired amount. So our doctor has ordered 200 milligrams. We divide by what we have. In this case, we have 160 milligrams, and that is in a quantity of 5 mLs. So we'll take a moment on our calculator to do the math. 200 divided by 160, and then times 5. We notice that the milligrams cancel, and so when we do the math, we have an answer of 6.25. The only label left is the milliliters, and so that's the label on our answer. We're going to repeat the same problem using the proportion. In the proportion method, the doctor has ordered 200 milligrams, and we would like to convert that into an unknown amount of milliliters, so we put X milliliters. We are making equal fractions, so we put an equal sign, and we use the 160 milligrams over 5 milliliters, which is the dosage strength, same information we used before. For the proportion, we multiply on the two diagonals, or cross multiply, and so I have 160x is equal to 200 times 5, which is 1,000. Then I need to isolate the x, so I divide by 160 on both sides of my equation. And 160's cancel, and again I have x equals 6.25. When I look back at the problem, my x had a label of milliliters, so my answer has a label of milliliters. The final way to approach this problem is with dimensional analysis. Again, we start with the doctor's order of 200 milliliters, or excuse me, milligrams. And we put that over 1 as a placeholder. In this method, we always want the labels to cancel, so I'm going to need to put milligrams in the denominator. So I put 160 milligrams in the denominator and the 5 milliliters on the numerator of the fraction. This way, the matching labels are in opposite parts and they do cancel. And so again, I go to my calculator. 200 times 5, divide by 160, and I get 6.25, and the label that remains is milliliters. So there are three different ways to do the same problem. You're only responsible to do a problem one way, so you can pick the way that feels the most comfortable for you. Let's try another problem. Again, the nurse needs the doctor's order. So we have an order for this med, 0.03 grams as an IM injection. Next, we need to look at what is available. So we find a container, and it has this label on it. Again, as the nurse, I'm looking for the dosage strength. How strong is this med? And again, it's in this darkened box here, 50 milligrams for every 2 milliliters. It would also be okay to use this reduced fraction. You would get the same answer either way. However, I do have a problem. The order from the doctor is in grams and the dosage strength is in milligrams, so I need to start off with a conversion. So I take the doctor's order, 0.03 grams, and I remember my King Henry. So King Henry died by drinking chocolate milk full of microorganisms. And this is grams, which is a base unit. It has no prefix, and I want to move to milligrams, so I move my decimal 3 places. And so this ends up equaling 30 milligrams. It is very important, no matter which method I use, that the labels between the doctor's order and what is available match, and that's why I switched to milligrams. So again, we're going to do the problem three different ways. Either way is acceptable, so do what's most comfortable for you. In the first way, the doctor's order is 30 milligrams. We have 50 milligrams, and our 50 milligrams is in a quantity of 2 milliliters. The milligrams cancels, so our remaining label is milliliters, and we just type this into our calculators. So 30 divided by 50 times 2, and we get an answer of 1.2 milliliters. Our next option is to do a proportion. So again, the doctor has ordered 30 milligrams. We would like to know how many milliliters, so X milliliters. Put our equal sign for equal fractions. We use the 50 milligrams over the 2 milliliters, matching up our labels, and then we cross multiply. So we have 50x is equal to 30 times 2, which is 60. We need to isolate the x, so we divide by 50 on both sides. 50's cancel, and we have x equals 1.2. We go back and look, and our original problem was in milliliters with our x, and so that is our label. The final strategy is to use dimensional analysis. In the dimensional analysis strategy, we start with the doctor's order of 30 milligrams. Put that over a placeholder of 1. We need the milligrams to cancel, so we put the 50 milligrams from the label in the denominator, and we put the 2 milliliters in the numerator, and we cancel the milligrams, and again we get an answer of 1.2 milliliters. Now, because this is an IM injection, we're going to need to give this in a syringe. So I have 2 syringes, and I need to pick the one that's appropriate. The smaller syringe only goes to 1 milliliter, so that's not going to hold the full amount. On the larger syringe, it goes to 3 milliliters, so it will hold the full amount. So here's 1, 1.1, 1.2 milliliters. So I mark my syringe and shade the amount that would be filled with medication. I think we have time for one more example. So again, we'll start with what the doctor has ordered. And this time the doctor has ordered 250 units of heparin as a subcutaneous injection. So we look for the heparin that's available, and again our most important piece is to find out how strong the med is, and it's in this darkened box, 1,000 units per milliliter. We have 3 different methods to calculate, and we'll go through each of them. In the nursing formula, we start with what's desired, which in this case is 250 units. We don't have an abbreviation for units, so I have to write out that whole thing. We have on hand 1,000 units in a quantity of 1 ml. And so again, these labels cancel. Our final label is 1 ml. We go to our calculator and we type 250 divided by 1,000, and we get an answer of 0.25 mLs. Our next method is a proportion. For a proportion, we want equal fractions, so we're going to start with a doctor's order of 250 units. And we'd like to know how many mLs that is, so X mLs. From our label, we have 1,000 units. I'm matching up the labels, so that's why this is on the top of my fraction, and that's in 1 milliliter. Again, I cross multiply, so 1,000x is equal to 250. I want to isolate the x, so divide by 1,000 on both sides, and again x is 0.25 mLs. My final strategy is the dimensional analysis strategy. Again, starting with what the doctor ordered, always the first part, so 250 units. Putting it over 1 as a placeholder. I want units to cancel, so I'll put the 1,000 units in the denominator, and I'll put the 1 milliliter on the numerator. Units then cancels because it's opposite parts of the fraction, so I'll take 250 times 1, divide by 1,000, and once again I get 0.25 milliliters. Now, subcutaneous injection. So again, this is an injection. So I have my 2 syringes. If I look at the smaller syringe, it will definitely fit there, so that would be a great option. If I look at the larger syringe, so 0.1, 0.2, 0.3, I really can't measure an amount this small very accurately. I could measure 0.2, 0.3, but I can't get the hundredths place, the 5. So I definitely want to choose the smaller syringe. 0.25 would be right about here. And then I shade the amount of medication. So we've gone through 3 different examples. We've done each of them 3 different ways. You need to pick one way, and you can do all of the calculations in the way that makes the most sense to you. So you can learn the nursing formula, you can set up a proportion, which we've done previously, or you can use the dimensional analysis, which we've also done previously, to solve a medication dosing problem.